Senior at the University of Connecticut. I'm studying math and physics, and I'm actually a particle physicist, which, even though it might not seem directly related to quantum computing, we actually use the exact same theory to describe things like protons and electrons that we do to describe things like qubits. And so I'm not as foreign to this field as I may seem. So today, what I wanted to walk you all through is what exactly is a logic circuit? How do we use them to solve problems? What is a quantum circuit? How do we visualize it? What are the most commonly used quantum gates? And how do we run quantum circuits on a real quantum computer? So first off, I wanted to start with a bit of an overview to classical computing, because quantum computing actually relies on a very similar framework. Classical computers have a fundamental processing unit called a bit, which is essentially just a 0 or a 1. It's like a switch. It's either on or off. These bits can be, like I said, either a 0 or 1, but on their own, they don't mean a whole bunch. We have to string them together before they can get super powerful and useful. And in order to solve problems, we send them through what we call logic gates, which convert zeros and ones into other combinations of zeros and ones, which we can then interpret as a solution to our problems. So I like to make kind of the comparison that an algorithm is a lot like a factory. We have our individual conveyor belts, which take in our products and make small changes to them. And those small changes happen kind of on a smaller scale than the whole factory. Logic gates are these kind of individual conveyor belts, making these small changes to the states of our bits. Whereas when we string together a whole bunch of logic gates, we get what we call a logic circuit, which is capable of carrying out an algorithm or solving some type of problem. So there are a whole bunch of examples of classical logic gates that we use in classical computing. The most famous one is probably the NOT gate. The NOT gate takes in the state of a bit and it spits out the opposite of that state. So if we take in a 0 state, it's going to output a 1 state. And if we take in a 1 state, we will output a 0 state. The NOT gate outputs whatever the input is not. And we can express this in something called a lookup table, which is very common for these classical gates. Lookup tables are just kind of a more condensed way for us to extract information about what exactly a gate does. On the left, we see the inputs, which are what we would plug into the gate, and the outputs column lists what we would get as an output from that gate. So this lookup table is saying if we input a 0 to the NOT gate, we will output a 1. And if we input a 1, we will output a 0. And this is great. This is a very condensed representation of what our NOT gate does, but logic gates can get much more complicated. Logic gates can have more than one input and more than one output as well. And the most important multi-bit logic gate that we're going to be using today is called the controlled NOT gate, or the CNOT gate. The basic idea of this gate is that there are two bits that play different roles. There is the control, which kind of decides what is going to happen. If it's in the 0 state, then nothing at all is going to happen to either of the qubits or either of the bits. We're still in the classical case right now. If the control bit is in the 1 state, then it kind of gives the thumbs up to apply the NOT gate to the target bit. And the target bit is specified with this other symbol. If the control bit is in the 0 state, then nothing will ever happen to the target bit. But if the control is in the 1 state, then we will apply a NOT gate to the target bit. And we can express this in a lookup table as well. The first thing I want to point out is these first two rows, which have the control bit in the 0 state. Notice that the inputs and the outputs look pretty much the exact same here, because nothing ever happens to the control bit. So the input 1 column and the output 1 column are the exact same. But in these two rows, notice that the input 2 column is the same as the output 2 column. And that's because since the control bit is not in the 1 state, nothing will happen to our target bit. However, in these two rows, you see that the control bit is in the 1 state, and we will actually apply a NOT gate to the target bit. And you could see here that now the input 2 column and the output 2 column are kind of opposites. Whatever is in the input 2 column is not in the output 2 column. So if we input a 0 as the target, we will get out a 1. And this is kind of an introduction to these more complicated gates. There are, of course, tons and tons of gates that we will not have time to look at and fully analyze, but there are tons and tons of classical logic gates that support kind of implementing different algorithms, of course, depending on the application. But what's more useful than to just analyze gate by gate is to string together these gates into something we call a logic circuit. In these logic circuits, we visually represent what an algorithm or a whole bunch of different logic gates are doing. And so we represent each bit in a logic circuit as a line. And so here we have 2 lines, and so this circuit has 2 bits. What I want to point out is over on the left here, we have kind of names that we assign to each of these bits. So the one on top is called Q0, and the one below is called Q1. It just makes it easier to refer to different bits in our logic circuit. Logic circuits are also read from left to right. So if we were interpreting a logic circuit that looks like this, we would first say that we apply a NOT gate to the bit called Q0. And then we apply a CNOT gate with Q0 as the control and Q1 as the target. And then we apply NOT gates to both Q0 and Q1. So I just want to review what we went over here. Logic gates are kind of these individual changes that we make to the states of bits in order to perform some type of larger goal when we string them together. And this kind of combined effort of all these different logic gates are what enables us to actually solve some problems. Now, quantum computers, like I said, operate on a very, very similar framework. However, there are some big differences that quantum computers provide that we need to take into account before directly applying this type of logic. If you've been to one of our workshops before, you might remember that qubits are the fundamental processing unit of a quantum computer. Sure, they can be in the 0 state or the 1 state, but those are kind of the boring ones since they exist in classical computing as well. Instead, what we're more interested in is actually this third type of state, which is called a superposition, which is essentially just a combination of both the 0 state and the 1 state. And instead of using classical logic gates, we use quantum gates to manipulate and change the state of all these different qubits that we might have in our quantum circuit. This is how we kind of transfer over that idea of logic gates and logic circuits into quantum computing. Something I do want to say is that for a lot of quantum gates, or pretty much all quantum gates, there really is no lookup table that will allow us to find out the final state based on the input state. And that's because there are actually infinitely many superposition states. And in order to fully understand the effect of the gate, we will have to list its effect on every single one of those infinitely many superposition states. So instead, we resort to some more abstract representations, such as the block sphere or matrices. Again, if you have seen any of our other programs, we talk about these a lot. But fortunately, we don't really need all of these abstract representations to understand a lot of what is going on in these quantum circuits. So I'm going to introduce us to our first few quantum gates, which are actually stolen directly from classical computing. So the NOT gate and the CNOT gate also have a quantum version, but they actually go by different names, and that is because of our good old friend, the block sphere. We call the NOT gate the X gate and the CNOT gate the CX gate. because that X refers to some type of effect on the Bloch sphere. Again, since we're not going into it, it might not make much sense, but just know that it is kind of standard to refer to the NOT gate as the X gate and the C NOT gate as the CX gate. But like I said, these are kind of the boring ones. There are some purely quantum gates that don't exist in classical computing. So let's take a look at one of those. This gate is called the Hadamard gate or the H gate. And what the Hadamard gate does is it takes a state that's not a superposition, so a 0 state or a 1 state, and it transforms it into a superposition state. Now, a superposition state in this case is one where there is a 50% chance of obtaining a 0 and a 50% chance of obtaining a 1. But it's actually a very common misconception to say that the H gate is doing some type of randomization, that 50% of the time it'll take a 0 state to a 0 state, and 50% of the time it'll take a 0 state to a 1 state. What's actually happening is that the H gate is taking this 0 state or the 1 state into a superposition. There's no randomness going on there. The only randomness comes when we implement this next step here. And this next step comes from a question that we might have about superpositions. You might be like, why have I never seen a superposition if it's a real thing? Well, the truth is we can't actually directly observe superpositions. So how are we supposed to get the result of a quantum circuit if we can't directly observe these superpositions? Well, we do what we call a measurement to force the superposition to essentially choose whether it wants to be a 0 state or a 1 state. And in the IBM circuit composer that we're going to use in a couple of minutes, you will see this symbol to denote measurement. And this is where the randomness comes in. When we measure a superposition, we have a certain probability of measuring the 0 state and a certain probability of measuring the 1 state. It is not true that after measuring a superposition, we will be able to detect the superposition or that we will end up with some type of superposition, because the act of measuring actually forces this superposition to what we call collapse into one classical state or the other. So whenever we take a measurement, we are always going to get a final state that is either a 0 or it's a 1. And so how do we kind of put this all together into something that is able to solve problems? Well, we will take our qubits or our fundamental processing units, we will take our gates and we will take our measurements and we'll shove them all together into a quantum circuit that we need to create to solve some type of problem. And so to kind of illustrate what we can do with these quantum circuits, I'm going to have us navigate over to IBM Quantum Experience, which is just a platform that we can use to design, build, and run our quantum circuits, because IBM actually makes their quantum computers publicly available. So anyone can go in and run their quantum circuits on their machines. So Shelby, if you could drop the link to the circuit composer in the chat. Again, if you have an account, you can log into that. You will be able to save your circuits. You'll be able to run your circuits on IBM's quantum computers. But if not, no worries. You can still use the quantum composer. It's not a huge deal. You just won't be able to save your circuits or run them on actual quantum computers. So if you navigate over to this link, what you will see is a screen that looks something like this. And on this screen, I know it looks kind of confusing and chaotic. That is perfectly fine. But let's take a look at kind of some ways we can simplify this first. Actually, I want to give you guys a second to catch up. I know I kind of talked at you for a little while. So just give me a thumbs up in the chat or like a heck yeah, let's do this in the chat if you are ready to continue once you see a screen that looks something like this. All right, I saw my first heck yeah. I'll take that as permission to continue. So something I want you all to do is close out of these two specific windows on IQX's interface. They are very useful for some people, but they are not going to be useful for us today. So I want you to click on these 3 dots here and these 3 dots here and click close window to make sure we don't have any clutter on our screen. It will make it a lot easier to interpret what's going on here. So I will do that on mine as well. I just click this here and I click close window. And I do the same with this Open Chasm 2.0 tab over here. I can click these 3 dots and click close window. And this will make everything look a lot cleaner. Yes, this will make everything look a lot cleaner and kind of not as messy because we are going to be working with some pretty complicated topics. And so I want to make sure that we have as little getting in the way as possible. So some things I want to point out about the layout of IBM Quantum Experience. You may recognize these lines in the middle of the screen. That represents your quantum circuit. Each one of these lines represents a different qubit. Up here on the screen, I'm showing 4 qubits. But something else I want to point out is that there is also another line, it's actually a double line, which actually represents some classical bits that we can play around with as well. We don't have any of that in today's workshop, but it is definitely a part of quantum computing to create some type of interaction between a classical computer and a quantum computer, since then we can kind of use the power of both to solve problems. I also want to point out that in these quantum circuits, all of the qubits and all of the classical bits by default will start out in the 0 state, which will kind of be important to us later on. For the first thing that we are going to implement, I want you to close out of all of the qubits except for 1. So you can do this by clicking on the names of the qubits, and you should have this menu here pop up. You should have a plus sign, which allows you to add another qubit. You should have a garbage can that'll delete a qubit. And then you have 3 dots, which we don't really need to worry about. But what I want y'all to do is delete qubit 1, qubit 2, and qubit 3, because we will only need 1 qubit for the quantum circuit we are going to start off with. So once you have deleted those other qubits, give me a thumbs up or a heck yeah, let's continue in the chat. And once I see a bunch of those, we will carry on. All right, I see the heck yeah train is picking up some momentum. I like it. All right, so let's continue. Now that we have only 1 qubit, our screen should look a lot nicer. But I want to point out another component of the screen, which has this label called operations. Here you might see some familiar symbols. You might recognize the H gate or the X gate or the CX gate, or maybe the measurement. All of these are possible gates that we can drag onto our quantum circuit and apply to our qubits, which we will do in just a second. But the last thing I want to point out to you all is that we have this kind of thing down here, which is a histogram of the probabilities of getting kind of certain outcomes for our quantum circuit. So this will help us represent kind of what's going on. And we'll kind of see how that plays out in just a second. So the first thing that I want you all to do, your first quantum circuit that I want you all to create, is this kind of simple quantum circuit shown here. You should have 1 qubit, and I want you to click and drag on the X gate over to the line representing qubit 0 and let go, and that will apply the X gate to that qubit 0. And I want you to tell me what changes about that histogram that you see at the bottom. What can you say about the probabilities of measuring either state? Yes, I see people saying that there is a 100% chance of measuring the 1 state. And that's kind of a very, I guess, expected result, right? We are starting off in the 0 state. We are applying an X gate or a NOT gate, and that is switching us into the one state. That's exactly what we would expect even from a classical logic circuit. So let's make this a little trickier. I want you to go back to your quantum circuit, and I want you to click on the X gate and delete it by clicking this trash icon here. And then I'm going to have you create a circuit that implements our first quantum gate, which is the H gate. And we will see just how this histogram changes. So I want everyone to click and drag on this red H gate over onto Q0 to apply the H gate to qubit 0. And then can I get some more responses that tell me what probabilities we have of measuring either of the two states? What does our histogram look like? Yes, amazing. I see people saying we have a 50% chance to measure the 0 state and a 50% chance to measure the 1 state. Now, this is just one representation that we can use to kind of display the results of our quantum circuit. But there is another one that's going to be particularly helpful for us called the state vector representation. So over on the bottom where you see your histogram, there should be a little drop-down menu that says probabilities. If you click on that, you should see two options. One that says probabilities, the other saying state vector. And I want you to click on the state vector representation. I want you to tell me if the state vector histogram looks similar or if it looks completely different from this current histogram of probabilities. Yes, it looks different, but it doesn't look completely different. I mean, we still see two bars. We still see kind of these two possible states. We see that the heights of the two bars are still equal. There's not one bar that's a lot taller than the other now. But this state vector representation actually touches on a deep connection between quantum computing and linear algebra. We can actually represent a whole bunch of quantum states as a vector, which is exactly what this diagram is trying to show. Now, these numbers are different. This thing we call amplitude is related to probability, but it's not exactly the probability. So this 0.707 that you're seeing isn't saying there's a 70% chance of measuring either state like we saw before with the 50-50. It actually turns out that the square of this number, so 0.707 squared, is actually 0.5. And that tells us that we have a probability of 50-50 to measure either state. So that is kind of an introduction to the state vector histogram. But an interesting result happens when we try to measure this superposition state that we have created. So I want you to click and drag a measurement over to the right of the H gate to create the quantum circuit shown here. And I want you to tell me what happens to your state vector histogram. Yeah, I see a couple different answers. Seems like some people are saying they measured a 0, and some people are saying they measured a 1. This is the nature of superposition. Every time we measure a superposition, each time we create and measure this superposition, we are imposing this superposition collapse. And you will end up with a final state that is either a 0 or a 1. Can anyone give me a guess of approximately how many people in the audience should get a 0 and how many people in the audience should get a 1 after running this experiment a whole bunch of times? Yes, I see 50-50. There should be a 50% chance that you measure a 0 and a 50% chance that you measure 1. And that comes from the fact that the H gate creates a superposition where there's a 50% chance of measuring a 0 and a 50% chance of measuring a 1. So this is a good place to pause for questions. Does anyone have any questions, I guess, about the content so far before we continue? I see someone was asking what a state vector means. A state vector is just another way that we can represent a quantum state. It's kind of difficult to see why it's useful to represent these states in a different way. But in the math, if we're doing all the equations out on paper, it does actually turn out to be a lot easier to use this vector representation than to use the probabilities. And I see someone asked, why does the IBM site show a 5,000 qubit simulator? That's because the simulators don't actually refer to real quantum computers. Those are classical computers that are pretending or simulating quantum computers. And so while real quantum computers are actually limited in the number of qubits that they have, we can kind of create simulators with as many qubits as we want. It just might take a lot longer to simulate the quantum computer than to actually run it on a real quantum computer. All right, I see a bunch of great questions. I will talk about the probabilities graph a little later, so I'm going to save that question for later. I also see some questions about the amplitude. Remember, the amplitude is referring to actually the square root of the probability, which is why the amplitude is equal to 0.707 before measuring, because the square of 0.7 is actually 0.5, and that's exactly the probability of measuring either the 0 state or the 1 state. And I see people also asking, does the H-gate always give me a 50% chance of either a 0 or a 1? The answer to that is actually no. We actually can apply an H-gate and end up with a different superposition. But the state that we need to apply the H-gate to isn't going to be just a 0 or just a 1. And so we actually need to create kind of more of a messy superposition state and then apply the H-gate. And then that way we will end up with a superposition state that doesn't always give a 50-50 chance of either a 0 or a 1. All right, I see a lot of great questions and I will continue answering them a little later. But just for the sake of time, I want to make sure we see a whole bunch of the cool quantum circuits. So I'm going to continue because I see another question that says, if we can never really observe superposition, how do we know that it exists? And that's a great question. The nature of superposition is every time we measure it, we get a classical result. We get a result that is either a 0 or a 1. So even when we observe a superposition, it doesn't quite seem like we observed a superposition because all we measured was a classical state. We never actually see the superposition. But based on all of the responses that you sent in the chat earlier, does anyone have an idea of how we can conclude that this quantum circuit does actually create a superposition based on the results of everyone's measurements? Yes, I see that people are coming up with the idea of taking lots of measurements. Exactly. That is exactly what we do in quantum computing. We run the exact same quantum circuit over and over to get a better idea of the probabilities of measuring either of the states. And once we do that a whole bunch of times, we will get a pretty good idea of the probabilities of measuring a 0 state and the probabilities of measuring a 1 state, even if we don't know what state exactly we are measuring. So this quantity of the number of times that we run a quantum circuit is called the number of shots, which we will see in a second, because where we're going is how do we run this quantum circuit that we just created on an actual quantum computer? So you might have noticed a button in the top right labeled Setup and Run. And that is the button that you're going to want to click to run your circuit on a quantum computer. If you're not logged in, you might see a button that says sign in to run your quantum circuit. And if you click that button, you will be brought to a login screen or a sign up screen that you can use to create and log into an account. But hopefully you've got that all done with at the beginning of this workshop. So I am going to continue with what you see when you open that tab. You should open up this other menu here that shows two kind of panels. On the left is a list of all the machines that we can run our quantum circuit on. We have simulators, which, like I mentioned earlier, are just classical computers pretending to be quantum computers. And those are all labeled with the word simulator, so there's no confusion about which is which. And then all of the other machines that they have listed, for example, here you see IBM Q_Lima, which corresponds to a real quantum computer that IBM has for us to use. Something I want to point out is the number of qubits shown right below the name. That will be important to us sometimes because we want to make sure if we have a quantum circuit that requires 3 qubits, that we're not trying to run it on a quantum computer that only has 1 qubit available. So this number of qubits normally would affect what machine we could run our quantum circuit on. But because we want to run a quantum circuit that has only one qubit required, we can run it on any machine that we want because all of the machines have at least 1 qubit. So once you select the machine on the left, I also want you to take note of this number called total pending jobs. These quantum computers are kind of first come, first serve. And so if we see that there are a lot of pending jobs, that means we're going to have to wait in line longer to actually run our quantum circuit. And so it might be worth kind of scrolling through all of the different options to see which one has the fewest number of pending jobs so that you can get your job submitted as fast as possible. On the other side of the panel, you will see that value called shots, which I talked a little bit about before. This is the number of times that your quantum circuit will repeat when you run it on a quantum computer. It doesn't really matter what number you put here. Of course, in practice, the bigger the number, the better. But there are some trade-offs, right? You can imagine the more shots we want to run, the longer it will take to execute. So there's kind of this trade-off of, do we want to have this really good understanding of what the state actually is, or do we want our results back quickly? But once you select a number, I would say select something between 1,000 or I guess you could do 100 and 10,000. Those are all pretty good numbers that you can input there. Once you do that, you can click on this button on the bottom right that says run on whatever machine you have selected. So can I get a thumbs up when those of you who wanted to submit your jobs do actually click this button and submit it to a computer? Or if you want to reboot the heck yeah train, you can absolutely do that as well. All right, great. So when you submitted your job, you might have seen something pop up on the left side of your screen. And it's okay if that went away. We're going to get it right back in a second here. But if you click on this little play button with an arrow around it on the left side of your screen, you will open a menu that will show you all of the jobs that you have submitted. For me, there are going to be a ton of jobs there just because I have submitted a lot of quantum circuits. But for you, there's probably only going to be one. So if you click on that job, you can get information about the status, where you are in line, if you're still waiting, if it's running on the quantum computer, and all of that fun stuff. Sometimes it will also give you an estimate of how long they think it will take before it does actually run on a quantum computer. Though recently I haven't been always getting that number. So it's okay if you don't see an estimate there. But once you get your results back, you're going to see another tab down at the bottom of that menu that says results. And that will give you an output to what actual results that you measured when you ran your quantum circuit. Now, someone asked earlier, why do we see all these random zeros here in front of the 1 and the 0? The answer to that is it's probably something that has to do with the programming. Maybe it's more convenient to format the numbers this way. Maybe I ran it on a machine that has 4 qubits. And so when we measured all the qubits, we get this output. But what I really want us to focus on is this number all the way to the right here, which is the 1 and the 0. And what this histogram tells us is that about 50% of the time we measured 0 and about 50% of the time we measured 1. And these are results from an actual quantum computer. This is an actual superposition that we just created and ran on a quantum computer. I see a question. Do we only get 5 jobs limit? So that is not a restriction that you can only ever run 5 jobs. Like you just used up one of your jobs. Oh no, that is concurrent jobs. So you can only run 5 jobs at a time. As soon as that other job is done running, then you can submit another 5 jobs, for example. So it's just 5 jobs in the kind of waiting line for any individual person. And that's so that we don't have one person clogging up all of the machines so no one else is able to use them. That's a great question. So, and yes, I see another great question, which is also worth bringing up right now. We do actually read the states from right to left. So the number all the way to the right actually represents the state of qubit 0. If we had the state of qubit 1 measured, that would be shown one number to the left of that rightmost number, and then we would keep adding on numbers in that direction. We call this right indexing, and it's particularly useful, again, for things like doing computations on paper, because not having to worry about what order we write the numbers in can really save us a whole bunch of time. And so if there are any other questions, you can feel free to ask those right now as well. But in the meantime, what I want you all to do is delete all of the gates from your quantum circuit right now. So click on them and click the trash can. And then once you do that, you should have kind of an empty quantum circuit. And I want you to add another qubit to this quantum circuit. So you should end up with 2 qubits because we are going to create an entangled state. So the way you do this is by clicking on the name and clicking on the plus sign. And that is going to give you those 2 qubits that we are going to need. Can I get a thumbs up in chat if you have 2 qubits in your quantum circuit now? All right, wonderful. So I will briefly talk about what exactly entanglement is. Entanglement is just a relationship between the state of 2 qubits where as soon as you have some information about one of the qubits, you automatically have some information about the other qubit. And I want to point out how strange this is when we think about something like flipping a coin. Let's say we have 2 entangled coins and their relationship tells me that the 2 coins will always land on opposite sides. So on one side, or on one coin, once we flip that coin, let's say it lands on tails. What the entangled relationship then tells us is that even before flipping the other coin, which should be a random process, I would automatically know that that coin would land on heads, which is strange. It's kind of removing some randomness. As soon as we have some information about one qubit, we automatically have some information about the other qubit as well. And so entanglement actually depends on us creating some type of relationship between the 2 qubits, which we haven't done any of so far. We've only applied 1 qubit gates. But can anyone think of a gate that we have discussed so far that would give us the opportunity to have the states of the qubits actually depend on each other? Yes, I see immediately in the chat people started saying the C0 gate or the CX gate. Absolutely. The CX gate will allow us to change the state of the target qubit by kind of picking the state of the control qubit. And that is exactly what we are going to do. But I want to give a quick disclaimer. Entanglement doesn't just mean that the states are the same or that they're different. Because if that was all there was to it, We could describe classical states like the 1-1 state, where both of the qubits are in the one state, as entangled, which is a little misleading, or at least it's not helpful. And so instead, we say that entanglement requires superposition. The point here is that the states are still related, but we don't know what the state of each individual qubit is. That is something we have to find out. And so the way we are going to create an entangled state is by having the control qubit in a superposition state. Because if we end up measuring the control qubit to be in the 0 state, we are going to do nothing to the target qubit. And because the target qubit started in the 0 state, it's going to end up in the 0 state. So in this case, we end up with both qubits in the 0 state. If we end up measuring the control qubit in the 1 state, then the CX gate is going to apply an X gate to the target qubit, which is going to flip it from a 0 state to a 1 state. So both of the qubits are going to end up in the 1 state. So no matter what, we are creating an outcome where both of the qubits are either in the 0 state or they're in the 1 state. So can anyone give me an idea of which combination of gates that we've talked about so far will give us this output of having the control qubit be in superposition and then applying the CX gate? Yes, I see all three. That is definitely a correct answer. I also see a lot of people saying the H gate and then the CX gate. Absolutely. This is the quantum circuit that will create entanglement. First, we use an H gate to put qubit 0 into a superposition state, and then we apply a CX gate that will change the state of Q1 depending on the state of Q0. So I want you to click and drag the H gate and the CX gate onto your two qubits to create this quantum circuit, and tell me what the state vector histogram now shows on your screen. What are the probabilities and what are the two final states we can measure? Yes, I see a bunch of people saying we will either get 0, 0 or we will get 1, 1. There is actually a 50% chance of measuring each of these possible outcomes. We don't know the exact state of either of the qubits, but we do know whatever the exact state is, the two qubits will always be in the same state. Now I want you to extend this a little bit. With this quantum circuit here, I want you to add a measurement to either Q0 or Q1. It doesn't really matter which one, but I want you to drag one single measurement. So you're only measuring one of the qubits, and I want you to notice what happens to the state vector histogram here. Yes, I already see two different answers. Someone measured a 1, 1 state, and someone measured a 0, 0 state. Again, we are collapsing the superposition, and we're doing this by taking a measurement. But we only measured one qubit, and that's kind of strange that we collapsed the superposition of both qubits. So let's create another superposition state. I want you to delete that CX gate and instead create this quantum circuit shown here, which is just an H gate applied to both of the qubits. What does this state vector histogram look like? How many possible outcomes are there, I guess is a good question. Yes, I see a whole bunch of people saying there are 4 outcomes. That is correct. This is what we call an equal superposition. We actually have an equal probability of measuring each of the different possible outcomes. But now I want you to do the exact same thing as before. Apply a measurement to just one of the qubits. So measure either qubit 0 or qubit 1. And I want you to answer this question. Do we gain any information about the state of the other qubit? In other words, does our whole superposition state collapse, or do we still have some superposition left over? Yes, I see a bunch of people saying we still have a superposition. by measuring Q0, or if you measured Q1, you collapsed that qubit superposition, but you did not collapse the superposition of the other qubit. And this is very different from entanglement, because entanglement means that when we measure the state of one qubit, we collapse the state of both qubits. So that is kind of the fundamental difference between having something like just a superposition and having an entangled state, is that with an entangled state, when we take a measurement of just one qubit, we will collapse the superposition of all other entangled qubits. Whereas if we just have a superposition state that is not entangled, then measuring the state of one qubit that's in superposition does not affect the other qubits that are in superposition at all. So that was a lot, and I'm sure you're wondering, where do we go with this? What is the next step? Or why did we bother doing all of this stuff? And I will admit, on their own, these quantum circuits didn't really do any meaningful computations. Sure, they were awesome. We got to see some really cool quantum concepts in practice. You are also free to run that entanglement circuit if you would like. I believe it will only let you run that circuit if you measure both qubits, though, but the effect will be the exact same. It's just kind of a formality that you need to do. But other than these circuits, the whole point of quantum computing is using these tools of superposition and entanglement to solve problems. And we have developed a whole bunch of quantum algorithms that allow us to solve a wide variety of problems. Some algorithms or protocols that use superposition include Grover's algorithm, which allows us to search for a correct answer in a long list of possible answers. There is an algorithm called variational quantum eigensolver, or VQE, which is used to find the structure of molecules, which is very, very cool in my opinion. There is also an encryption protocol called BB84 quantum key distribution, which helps encrypt our information so strongly that not even another quantum computer can hack and access that data. And then there are also a whole bunch of algorithms and protocols that use entanglement. We can do quantum teleportation, for example, where we are able to teleport a quantum state from one place to another just by using entangled qubits and photons, which is very, very cool. There is also another type of encryption called E91 quantum key distribution that, instead of relying on superposition, relies on entanglement. And then we also have an algorithm or a protocol called entanglement swapping, which allows us to essentially double the distance at which we can entangle two qubits. So we can end up having qubits all the way across the world by doing a whole bunch of entanglement swaps. And if you're interested in learning anything about any of these quantum algorithms, we explore them to various extents in all of our different programs. We have our year-long course in which we will dive a little deeper into all different aspects of quantum computing, from the math to important algorithms to the actual construction and what quantum computers are made of, all of that interesting stuff. We also have a whole bunch of different summer programs ranging from middle school to teacher and professional development. And we also have different workshops and initiatives and hackathons and all of these really exciting programs within Qubit by Qubit, and even a whole bunch outside of Qubit by Qubit, like Shelby mentioned at the beginning. We have our train program in which we dive deeper into machine learning and AI as well, which is extremely interesting and kind of cutting edge. And so if you're interested in any of that, Shelby will send out an email following up with a whole bunch of information about all of our programs. You can also find information about our programs on our website, which we will drop in the chat in just a second. And of course, we also have workshops. I think I mentioned it already, but we have workshops just like these where we go over into some niche topics in quantum computing and in other areas as well. And yeah, hopefully you gained something from coming to this workshop. I want to thank you all so much. I hope you learned a thing or two about quantum computing. And if we have an extra minute or two, I will definitely answer some questions that I see have been piling up. Yes, so thank you so much, everyone, for attending today. I really, really appreciate seeing how many people just showed up to learn a bit about quantum computing.
Yeah, Ricky, maybe if you want to take like 2 more minutes, if you're cool with that, and we can answer a couple
absolutely.
questions. Cool.
Yeah, so.
And if you guys don't want to stay on, you can feel free to drop. We've completed the workshop, but we'll just answer a few questions. So thanks everyone for coming.
All right, I see an interesting question. Do I get a choice of what type of computer I map to? Normally we map to a binary based computer. What about one of those Russian ternary computers? So those are computers that instead of just having a 0 state and a 1 state, they have a 0 state, a 1 state, and a 2 state. So now we actually have 3 options. And unfortunately, these types of ternary computers are very difficult to work with. And so we normally kind of focus on these binary computers that we've worked a lot with just because we have been developing them for a lot longer than these ternary computers, and we found a lot more success. So unfortunately, our only option right now is to map to a binary based computer, but that is a great question. Let's see. Another interesting question, how accurate are the simulators compared to the systems? Can we rely on the results of simulators? So the answer is yes and no. The simulators are doing some linear algebra type computations to try and figure out what the final state should be. And then it uses pseudo-random numbers to try and figure out what the random result of a measurement would be. So it's accurate in the sense that it's doing the math correctly and it's simulating this randomness, but it turns out that simulating a quantum computer is super, super computationally expensive. And at some point, even the most powerful supercomputer in the world couldn't simulate what a quantum computer could do in milliseconds. So that's why we're really focusing our energy in developing these quantum computers, is because we don't have to use the best supercomputer in the world to solve these problems anymore. We could use any old quantum computer that we have lying around to solve these problems, which will make these types of problem-solving methods a lot more accessible. Great question. And then let's do just one more. I see a whole bunch of questions, which I'm really happy to see. Yes, I'll wrap it up with this question, which I always get, and I understand why. Can quantum computers replace classical computers in the near future? The answer is, if anyone tries to give you a definitive answer, yes or no, it's just a guess. No one knows where this technology is going to go. There is definitely a possibility that we could all be walking around with a quantum laptop somewhere in the near future. And there's also a possibility that it's just not feasible. We don't have the technology or the understanding of these systems to be able to actually shrink it down into a small enough system that we could have it in our houses. So it's kind of a gamble. It could go either way. There's a possibility that we could eventually have quantum computers sitting on our desk, and there's a possibility that they will be reserved for something like a cloud computing service where we could send our jobs off to be solved on a quantum computer, but we don't actually own it. That's where I kind of think things will go, just because of how expensive developing a quantum computer can be. But of course, I am not a prophet. I am not an oracle. I can't see into the future. And so I would not be surprised if my guess is completely wrong and we end up in kind of a completely different world when we are able to kind of refine this technology further. Again, a very great question. And unfortunately, that is all the time we have for questions. Again, I want to thank you all for being here. If you have any other questions, they will probably be elaborated more on in some of our other programs. Again, shameless plug. If you want to enroll in any of our programs, we will definitely send out more information on that. So thank you, everybody, for attending this workshop today. I really, really appreciate it. And hopefully I will see you in one of our future programs. Bye, everyone.